for the broadband network, working on Tier 1 MSOs for the smaller region operators in 7 countries across the globe. He's an experienced engineer holding a master's in telecommunications engineering from the University of Zaragoza. So he's going to be doing his presentation. If you guys have any questions, please be sure to enter them into the chat. I also want to note that our presenters today, Diego and Abba, are calling in from the Netherlands. It's midnight their time, so we really appreciate them staying up late for us. And we're looking forward to your presentation. Thank you so much for joining us.
So I guess it's good afternoon to everybody. I want to say thank you for this opportunity to be here with all of you, to all the attendees. And I will try to make a presentation about DOCSIS 4.0 networks and how can we evolve these, the current networks that are all over the world to face all the challenges that DOCSIS 4.0 can bring. So as it was said, if you have any questions, please interrupt me. Yeah, let's go with it. So the idea of DOCSIS 4.0 is the final goal of DOCSIS 4.0 is to deliver 10 gigabit in our networks. So there's 2 different ways on the way we can do this. Is we can go through the route of full duplex DOCSIS or through the route of extended spectrum DOCSIS. They both have these pros and cons. I think if you ask me right now, ESD is the most the trend that most of the people wants to follow. But these 2 standards or technologies, they have to be implemented. DOCSIS 4.0 is able to implement them in the standard. So full duplex DOCSIS, the idea is to use the same frequency for the downstream and the upstream. We can give this capacity in both directions at the same time. The advantage of full duplex DOCSIS is that the network stays up to 1.2 GHz, so it's something that is more known. And so the passives can be still the same. And it's a really, it's a more efficient use of the bandwidth. One of the disadvantages of full duplex DOCSIS is that you have to your passives has to have a really nice isolation between ports to have the matched number of interference groups. Our architecture has to go M+0 because we have to have elements without diplex filters. And it can be an expensive rebuild, especially to bring fiber deeper to have M+0 architectures. ESD, on the other hand, the idea is that I go higher in frequency up to 1.8 GHz, and the upstream can go even up to 684. So the idea is that we have more spectrum to share with the upstream and with the downstream. Challenges, the advantage is that the structure is quite similar. We don't have to, we have to use the same actives, well, not the same, we use active, we use passive, we use cable modems without full duplex DOCSIS capabilities or small computers that has to deal with upstream, downstream at the same frequencies or etc. Can still be built in M+3, M+5 networks. And I think, as I said before, I think it's more accepted. I think the trend is to go more to ESD rather than full duplex DOCSIS. And disadvantages, we'll see it later. Losses are go extremely high. We can have an impact on the power consumption. And we have to upgrade all the components for the not only the actives, but also the passives, cable modems, etc., etc. But since, as I said, the trend is standard spectrum DOCSIS, I will go right now to, I focus more in the standard spectrum DOCSIS. If we have some time, I also have some slides for full duplex DOCSIS, but depends on the audience and also depends on the times that we have over here. Standard spectrum DOCSIS, we think as a network right now with active tabs to distribute the signal and the houses, we have several challenges. First of all is the cable losses. They go higher, but also the passives that we have, like the tab losses, they also go higher. We have to deliver a higher signal, so that means that is an impact on the total composite power, so the energy that an active element can manage. in the actives like amplifiers or remote PHY or remote MAC-PHY devices, but also in the cable modems to transmit the upstream signals. And we can, because of the losses that we have, the extra losses that we have in the passives, we can have noise issues when we don't receive enough level. So to put some numbers to these ones, approximately we can estimate that the losses, the typical losses that we can have when we go from a network to 1.2 gigahertz to 1.8 is 25% extra. So we have 25% extra losses only in the cable. We have to take into account that every passive that we introduce, like a tap or a splitter or a directional coupler, can be more or less half a dB, in some cases even more. And so the total loss, we have huge loss that we have in total, then it can be even up to 15 dB extra. So if we get all these elements or all these extra losses that we said, we can need even 15 dB extra level to reach the houses as we were used to do before. And also we have another problem, as we said before, is the total composite power that the actives can deliver. At the moment, in the current state of the art, amplifiers of 1.2 gigahertz can deliver a maximum of 74 dBmp of total composite power, and we can reach 3 dB extra if we double the power consumption. That's the best thing we can do with current state of the art of the hybrids up to 1.2 gigahertz. But at the moment, up to 1.8 gigahertz, the reality is that this TCP is even lower. So we are saying that we need 15 dB extra, and the best we can do is have around 75 dBmp of maximum total composite power by doubling the power consumption in the actives. So we can only deliver 3 dB extra by doubling the power consumption, and the 15 dB of losses, they are not over there. And we also have to include that this TCP that I'm talking about is in the chip. Inside the amplifier, we have to deal with the test point, the diplex filter, etc. So this can be even 3 dB of internal losses. So as you see, for the downstream, the initial scenario to go to standard spectrum DOCSIS can be a little bit difficult. For the upstream, something similar. So if we have at the moment a diplex of 42 megahertz and we want to evolve to 204, the extra losses is 100%, so double. And if we calculate what's the losses from 204 to 684, that is the latest stage of DOCSIS 4.0, this is double again. If we try to calculate an average network, let's say that we have 40% of the losses are the cable, 60% are in the passives. So we would need from 16 dB gain of 42 megahertz to around 21 dB gain of 204 and up to 30 dB gain extra in 684. But the reality is that this is much more easier because at the moment we have chips that can deal with these frequencies. So there's much more market to select the chip that we want to do to deliver these signals up to 684. So the way we overcome all these challenges for DOCSIS 4.0, for the networks that are able to deliver DOCSIS 4.0 signals, we separate them in 3 types. We say that we have network with high power amplifiers. So that's what I was talking about, before. Deliver 3 dB extra or deliver the maximum an amplifier can deliver at the moment by doubling the power consumption. We have medium power amplifiers. So that means that these are regular amplifiers like we know, like the current amplifiers that we have 1.2 gigahertz with 44 dB of gain, etc. With the support of a booster amplifier. So this is a small element that has small gain, and its use is placed between 2 big amplifiers to boost the signal a little bit. So we help the signal to reach the next amplifier or to reach the cable modems, or what we call distributed gain architecture. So this is rebuild the network completely with these small booster amplifiers. And we do how we do it special, because booster amplifiers already exist in the market for years, is that we build amplifiers, this kind of booster amplifiers without diplex filters. So like the one that you have on the screen, you see two lines, the blue line that is the upstream up to 684, and then the black line that is the downstream. They are completely overlapped. So this is an amplifier without diplex filters. So if we don't have a diplex filter, we don't have any guard band. We don't have, we can have more data throughput because the upstream can finish at 684 and the downstream can start already to 684. So that's almost 150 megahertz more than than the 684 834 that is the latest duplex duplexer of DOCSIS 4.0. And we can implement technologies like full duplex DOCSIS or flex split, for example. So I'm going to explain a little bit these three options: the high power, mid power, and DGA. And I will show you also some numbers that I measured in the lab with some measurements that I did in these three scenarios, and to see what can happen when you implement this kind of architectures in your network to deliver DOCSIS 4.0. So if we think about how we build networks, we have amplifiers, we have the taps that deliver the signal to the houses, and then we have the level in blue of the level that the amplifier delivers. And then here at the bottom, we see the level that these houses delivers. So we have to be really clear that one thing is the level and the other is the quality. So to show this, we know that the actives can work in different areas. So if we deliver too much signal, too much TCP from an active, we are going to drive it into saturation into the saturation area. So that will have a huge impact on the quality that we have in our signal. This quality is never recovered. There are no amplifiers that recover quality. Otherwise, I will be winning the Nobel Prize of Physics. So if the quality of the first amplifier is impacted, this quality is going to travel to the houses. But then if the houses receive a level down the noise floor that they have, like in the drawing that we are seeing in this red area, this will also again have an impact on the quality. So it's important to deliver, it's as much important as deliver enough signal for the cable modems and then having a good quality from our actives. So if we think in a 1.2 scenario, at the moment, the levels that we can deliver from the amplifier are in this green area, what we call the safe area, when it's away from the noise and away from the saturation. If we go to DOCSIS 4.0, so if we extend these levels to 1.8 GHz, then we find that the amplifiers can reach this saturation area because they have to deliver much signal. And then when we measure this signal in the next amplifier, we see that we fall into the noise area. And the same can happen with the taps, that the first three taps in this example, and in this drawing, have enough level to be above the noise area. But the last two taps, we can have some problems. So the good thing or the advantage of using this kind of equipment is that we can maintain the same structure. So in the same positions that we have the amplifiers, we place these new amplifiers, and then it's way more simple. We don't have to recalculate the network with new tap values. Everything is as it used to be. But we have the problem of the noise and the intermodulation. This, of course, won't happen in all the networks, but that can happen. There will be networks that will have up to 15 dB extra losses. And by doubling the power consumption, like in this case that I'm using line extenders of 40 watts, I don't have enough level to deliver. And I force my amplifier to work as hard as he can. So this can be a problem in some cases. And also another challenge that this kind of architecture has is that we have huge power consuming elements in our network. This means more heat that needs to be dissipated, more stress into the power supplies, and they can be damaged. So we need to have maintenance. We have to send technicians to repair these amplifiers or the power supplies of these amplifiers. They are not going to live for longer because they are working really, really hard. So Another thing that we can do is, as you can see, if TCP is my problem, what I'm going to do is I'm going to maintain my structure up to 1 gig or the legacy frequencies that I was using at the moment. So I give the same, exactly the same service to the customers. But then the part of the DOCSIS 4.0, so let's say the OFDM blocks that we introduced from 1 gig to 1.8, we reduce it. We make like this step down. So in this way, we solve the problem of the TCP, but we will have more problems because then suddenly the frequencies that need extra level are going to be reduced and going to be stepped down. So I'm going to have much more problems with the noise in the cable modems or in the next amplifiers. And I see another problem, and I will show you. This is some measurements that I did. I built the network that you see on top. So an amplifier with different meters of cable or feet of cable in tabs in between. And then I measure, I use a drop cable simulating the drop that you will have in a network. And then I measure these levels, that is this graph that you see over here. This simulates the levels that a cable modem will receive at their input. And then you see that the tab number 1, the tab number 2, and the tab number 3 are fine. I put the limit in 0 dBmp. So you see that they are quite okay. But then you see that the tab number 4 and the tab number 5, they already have a lower signal. And I see also another problem, that is the equalization. Because now tab number 4 and tab number 5, they need to be equalized. So that means that even though the legacy frequencies, so the frequencies below 800 megahertz or 1 gig are above the threshold that we set, they need to be equalized because the cable modem are not going to understand a signal, for example, the blue line of the tab number 5, a signal with 20 dB of tilt. So I need to attenuate the low frequencies, and therefore these frequencies will go under the threshold. So this is something that we need to think about when we do the network calculations, when we evolve a network to DOCSIS 4.0, and we use this architecture. This is what we're saying. So what happens if we do the step down? The step down makes things even worse. As I was saying, yeah, legacy signals are about thresholds. They are okay. But now my DOCSIS 4.0 signals, they all fall below the threshold. And the same problem that I had with the equalization of the low frequencies in the last tabs, that they receive a signal with huge tilt, this becomes worse because now my tilt, instead of being 20 dB of tilt, is 26 dB of tilt because of the step down. So I need even more equalization. So I'm going to bury the low frequencies more into noise. So this is something that we really need to think about when we try to use this architecture. The advantage, same structure, no complications. It's like keep working the same way that we're used to. But the problems, we are already seeing them. Amplifiers being forced to work really hard and levels that can be problematic in the cable modems. Another architecture that we want to show. No, this is another thing that we can do, because if we don't have enough level, basically what we have to do is respace the amplifiers. Then we have enough level into the cable modems, into the next amplifier, etc. I don't have problems with the TCP. I can do the step down, no problem. But then we lose the advantage that we have. We cannot use the same structure anymore. We have to disconnect the amplifier, install it in another place, and create a new power position, for example. So I think this is absolutely a no-go. We cannot do this wherever we want it or not. The other architecture that we were talking about, what we named mid-power amplifier plus booster. So the idea is that from the first amplifier, I don't have to do the double power consumption amplifiers. I can still use regular amplifiers, mid-power amplifiers. For example, in this example, I use with 19 watts elements, because this one doesn't have to deliver all the signal. He has the support of the booster amplifier. So a small element of 6 watts that we put something in between these two amplifiers. So when the signal starts to become lower, we boost it up a little bit. So we are away from the saturation and the noise area. And then we reach the next amplifier with enough level. The same would happen in the houses. we have enough signal in the first 3 taps, and then in the last 2 taps, we push the signal a little bit, so we have enough signal. So, in terms of a structure, can be a little bit complicated because no, it's going to happen. You will have to change the value of the tap number 4 and the tap number 5. You have more signal, you have to increase the value of the tap. So instead of being 14 and an 11 dB tap, it needs to be maybe a 20 and 17. So the network designers have to take this in account, that these taps needs to change their value. In terms of quality, it goes better because now the first amplifier or the big amplifiers, let's say, they don't have to deliver a high signal. They stay away from saturation, even though they introduce intermodulation because they use hybrids inside. But we don't force them that much. And then we use mid power. So from maintenance perspective and power consumption, this becomes better. If you think about the first example, I have 2 elements of 40 watts. Now I'm using 2 elements of 20 watts each and 6 watts. So the power draw makes more sense in this scenario. And remember the problem that we talked about equalization? This solves a little bit because the booster amplifier has a tilted behavior. Oh, wait. You see that now all the taps are over the threshold that we set of 0 dB MV inside the cable modem. And the tab number 5, that is the light blue line, and the tab number 4, that is the yellow line, they are flatter. They don't need equalization because they are more or less flat. So we also solve the problem of the strong equalization. And we don't need to use the step-down strategy because the first amplifier is going to work out of saturation. They share the fault between the booster amplifier and them. It's the same way you compare these first two architectures. If you compare it the way you run a marathon, and you don't finish a marathon by making a huge sprint, and when you are too tired, then you make a huge sprint again. That is what the high power amplifier would do. You make a constant speed. That is what this architecture would do, and then you finish the marathon. The other way around, you cannot. So what if we go from high power amplifier to distributed gain architecture? Distributed gain architecture basically is getting my traditional amplifiers, strip them in small amplifiers and place it all over the network. So I use the gain as I need. So in this example, instead of having these big elements, every time I run out of level, I place a small booster, I boost the signal a little bit, I make them stay away from saturation and noise area, and then I continue all over the network. And then I can deliver the signal to the houses above the noise, above the 0 dB MV or whatever threshold we put, because basically when we don't have enough level or we don't have enough gain, we place one of these amplifiers. The disadvantage in terms of structure, this is a complete redesign. So the network designers have to work again really, really hard because they have to evaluate in which positions of the network I can put on these booster amplifiers. Every time I need the level, maybe there's not an access point in the place that I want to put it, so I need to put it in another place. So it's a nice exercise to do for the design perspective, but can be worth it. Because in terms of noise and intermodulation, the quality is perfect. These amplifiers work really, really, really smooth. They don't have to do any effort. They just have to work. They work really smooth. They don't barely have an impact on the quality because they stay away from saturation, and they stay way away from saturation. And in terms of power, even though we are adding much more small elements, we have less power into the network, and then that means that there's less heat, and then that means that there's less maintenance. Everything works smoother. Works like they are on holidays, let's say. So it's from maintenance perspective, this is a cost that DGA could save. And if these booster amplifiers have no diplex filters, the huge advantage is that you build this network and you don't have to touch it at all in 30 years or 40 years. or when we go to 3 GHz, who knows? And because yeah, the theory under this is that the amplifiers, you don't have to change it because they are going to live quite a long life because of their lower power consumption, no diplex filters. So every time I need to do an upgrade, used by software, I select the diplex, the frequency that I want for the upstream, the frequency I want for the downstream. I can even glue them together, and job's done. But to build distributed gain architectures, it's not like having only booster amplifiers. We estimate, or we make a lot of calculations, and we find out that to make distributed gain architectures, we need different blocks. We need to be flexible to adapt our network to DGA. So the first element that we need is the booster with high level. And in case that the access point to install this amplifier, it's closer, let's say, to the remote PHY or the remote MAC-PHY device, or when the signals are still higher, we need an amplifier that can deal with higher level. So this wouldn't have an extra power consumption, but we can also use it to make AGC or ASLC capabilities. So to have temperature stable algorithms inside this amplifier to maintain this network stable. Because if we don't have them and we build this network with only simple boosters, then the temperature is going to hurt us quite high. So we need to install these kind of elements at different parts of the network to compensate for the temperature. The next element is what we call the zero loss or the zero loss splitter. That is an element that you can see over here. They have this is a 3-way splitter with 0 dB losses. So you can see it's completely flat, and then the upstream and the downstream again are overlapping together. This helps because the problem with booster with tilted behavior or anti-coax behavior, that what this booster do, is that the gain in the low frequencies is quite low, the same way as the cable has lower losses in the low frequencies. But when we have distribution elements like splitters or directional couplers, they have a flat loss in all the frequencies. So imagine, for example, that this booster amplifier has a gain of 3 dB in the low frequencies, but my splitter has 4 dB of losses. This booster amplifier is not going to compensate for the losses of the splitter. So that's why we need an element like this, a booster zero loss splitter. So it's not like we gain something, but at least we don't lose 7 dB or 7 dB in a 3-way splitter. The next element is the regular booster, let's say, that it's we can put it somewhere intermediate in the network. And for the cases that, for example, we have the last stop in our network is really far away, we can use the low noise version, and so we use it to give enough signal to the last stop that is in really long distance. So with these 4 elements, we can build DGA. But not only DGA, these 4 elements are also good if we go for, let's say, a traditional build. What we were talking about, if we have some 15 V extra losses, because we have, for example, a 3-way splitter somewhere, even if we use the traditional build with regular normal amplifiers, let's say, we can use this booster element to reduce the losses in the splitter. Or in a traditional build, if we have the last stop in the cascade is like, I don't know, 1,000 feet distance from a known position, instead of it doesn't receive any level, instead of installing a huge line extender just to serve that last stop, we can use the low noise version. So even these 4 blocks can work perfectly in a traditional architecture. They will help us to reach DOCSIS 4.0. They will help us to reach 1.8 GHz. So I want to show you, don't make much effort, because I wanted to show an exercise that I did for DGA for an existing node. So I basically received this node from one of our customers, and they asked me if I could transform them into distributed gain architecture. So to make this node a little bit more focused, in one of these parts of this node, I have this example. So I have the 44 1.2 GHz amplifier with a three-way splitter that continues to a two-way splitter and distributes the signal in all these tabs. So basically, in this part of the network, what I did was to strip this 44 dB gain amplifier, and I built something like this. So in the same position that I have the traditional amplifier, I place a small booster. Then this three-way splitter, I change it by a zero loss splitter. And then I place booster amplifiers whenever I need them to deliver signal to these two of these tabs. So basically, I'm stripping the 44 dB gain 1.2 GHz amplifier by two small booster amplifiers. So I have this path, I need two amplifiers to this path, two amplifiers to this path, two amplifiers, and the zero loss splitter. So I have a total of 30 dB gain at 1.8 GHz and with a zero loss splitter. So I use the gain in much more efficient way. I put the gain as I need. Instead of 44 at 1.2, I'm using 30 at 1.8 GHz. More efficient. Sorry. The result of this whole node built in DGA is what you can see on these graphs over here. I have the cable modem receive levels and the cable modem transmit levels. So you can see that all the cable modems that I connect in this architecture were below 0 dBm, 100% of them, didn't fail a single one. And all the cable modems were transmitted with 50 dBm, that it was what we put as limit. So DGA, in this case, was possible to be built by using the combination of these four elements. And what we were talking about of redesigning the network, this network was built by changing 56% of the tabs. So half of the tabs that were in that network needs to change the values. So this is what we mean with extra exercise, or it's not so traditional, or the designer needs to do the exercise of these networks. But again, if we build this network with DGA, we don't have to touch it anymore. We don't need to do any change. Everything can be, all this, the split can be controlled by software. So another point or another comparative, because this was more a comparative in terms of levels, qualities, etc. I want to make an example of these three architectures in terms of power consumption. That is, of course, an important cost to take care. So imagine we have a city with 50K homes passed, and we have the different architectures. So, for example, with DGA, we need, I don't know, 4,500 amplifiers of 6 watts. And then we introduce a percentage values that simulates the I square R losses in the cable. In the mid power amplifier plus booster, we need 2K line extenders of 19 watts. And we need 2K booster amplifiers of 6 watts. We need extra current, so that means that I square R losses, I estimate that is 10% more. And then with high power amps, so in this case, we have every time high power amps, double power consumption. I put them whenever I need them. I need only 2.5K amplifiers of 40 watts. And since they need extra current, I estimate 20% cable loss, I square R loss in the cable. So if we do the numbers, we see, let's say, to compare the more power to the lowest power, we calculate that this could be 100,000 watts versus 28,000 watts. So 100,000 watts less if we go to DGA. If we go from high power amp to DGA. And sounds a little bit crazy because it's like, oh, we have more amplifiers and we have less power or less current, or I have to pay less to the electrical company. But it's the whole idea of distributed gain architecture is the distribution part of DGA, you know, because it's not like we have one big amplifier versus small amplifiers. The big amplifier itself has three different stages, has the pre-stage, interstage, and then the hybrid. So instead of having these three stages in the same location, I stripped them in three and then I distributed all over the network. So it's not like DGA has more amplifiers, it has more positions, but in terms of amplifiers, it's more or less the same. And yeah, if we compare the general result, we say that the level is good because in all these scenarios it's let's say an ideal network, so we have leveling everywhere. Well, it's okay. The MTBF we estimate 18,750 hours, and the power, if we divide the power per homes passed, it's 2.5 watts. In the medium power plus booster, level is good, the quality is better than the high power amplifiers. MTBF goes higher, almost to the double, and the power is 1.1 watts per homes passed. And then when DGA kicks in, level is good, the quality is good, all the amplifiers work really smooth, as we said before. MTBF goes to 142,000 hours. And the power that we have per homes passed is half a watt per homes passed. So it really, really makes the difference if we think about these numbers. So we saw the network, in terms of level, in terms of quality, and we saw the networks in terms of power consumption and maintenance, of course. We know the less the power, less it dissipates, better for the maintenance perspective. So if we want to try to, let's say, summarize, and we have to compare these architectures. So if we see the high power amplifiers, it's a really practical network. It's what we are used to build. So in terms of practicality or practically, it's good. But in terms of TCO, that means power consumption, maintenance, price, etc., it's not as good as the others. And in terms of performance, yeah, we have problems of the TCP on the amplifiers. We will have amplifiers working really hard, really close to saturation or even in saturation. And sometimes we don't have enough level to deliver to the cable modems. In terms of mid-power amplifier plus booster architecture, it's more or less the mid-term. It's not as easy as the normal, let's say, architectures or the architectures that we are used to, because we have to install a booster amplifier. Maybe you have to change one tap value or something like this. But yeah, so we are midway. TCO works better, consumes less power, better for maintenance perspective. In terms of performance, works better than the high power. I'm going to have enough level for sure, because every time I don't have enough level, I will add a booster amplifier, and the amplifiers, let's say traditional amplifiers, they don't have to work that hard. And then we have DGA, that in practical point of view, it's much more difficult. We have to redesign the network. We need to change tap values. We need to evaluate if we have position to install a booster amplifier, if we have an access point to install them, etc. But in the other hand, in terms of TCO, so the power consumption is going to be way lower. And in terms of maintenance, it's going to be way lower. In terms of upgrading the network, it's going to be way lower, because we don't have to do anything to the amplifiers or to the access network in general once that this network is created. And in terms of performance, is the best, because the amplifiers work really smooth out of saturation. They only have to take care of the noise. So as I said, it's not like you have to build your network you have to choose, between one of the three alternatives. It's more to know what are the things that you can do in your network. And some networks, I don't know, can work with high power amplifiers or can work in a traditional way. And no problem, because the distances are not that much, etc. But other networks that can be more complicated, maybe it's worth to try DGA, because on the other hand, the other architectures, they won't work at all, because I don't know, the distances are too much, many taps, etc. So it's not about that you have to choose one. Every node that you have in your network can be built in you can choose whatever you want. So this was my part for extended spectrum DOCSIS. I don't know if there's any question.
Nothing yet. If anyone has any questions, please type them in the chat.
Mm-hmm.
Okay, here's a question. What's the status of availability of 1.8 gig passives?
Which at the moment, yeah, I could have included some product specific. We have 1.8 GHz passives in production. And the way we do it in Technetix is we made it in a different way. Our passives, our 1.8 GHz passives has 3 GHz backplate. So our passives are ready for 3 GHz. And then in the faceplate, we have a plugin to select the value of the tap. So in general, I mean, our passives, we have the backplate. We have 3 different faceplates for the 2-way taps, 4-way taps, and 8-way taps. And then we have only one, we have the plugin that selects the value of the tap. And in this way, we reduce the SQTs that you can have. And I think they are already in production. So for sure, they are ready to test.
Cool, thank you. Here's another one. Is any special consideration necessary for AC bypass coils on those 1.8 gig passives?
I'm sorry, can you repeat again?
Is any special consideration necessary for the AC bypass coils on 1.8 gig passives?
Well, the problem that we are facing, and I think it's also general in the industry, is what exactly what I say. The power coils cannot work anymore from 5 MHz if you want to go to 1.8 GHz. You normally have to start between around 12, 15. Well, they can still work from below 15 or 12 MHz to 5, but we have some return losses. In the return losses, we have worse characteristics. But in passives, normally when you install 1.8 GHz passives, you should be already considering going to high split. So, for example, if you install your 1.8 GHz passives, when you go to the high split of 200 MHz, you are not going to notice these losses in the return loss bar or below 15 MHz. You can start easily from 12 MHz or to 15 MHz up to 200. So we know that it's a trade-off for the design, but there was no other way we could overcome the problem with the power coils of the passives.
Okay. There's another question here. CPE cabling can be creative. Have you tested CPE impacts at 1.8 gigahertz?
As far as I know, not at the moment. This is a question that I would need to ask to the quality engineers.
Okay. Well, I think that that's it for questions. Thank you so much for your. Oh, never mind. One more came in.
Right.
Another question related to the AC bypass coils.
All right.
What's the maximum current capacity of each passive? 5 amps, 10 amps, 15. What is it?
At the moment, we are testing 15 amps.
Okay.
Yeah, that's the idea that we wanted to have for sure. As we have seen in some of the networks, the power draw is going to go quite high, so we definitely need high current passing and all over our passives. Yes.
Great. Well, thank you again.
Yes.
For taking the time, and yeah, I know it's like after midnight there, so definitely appreciate
tomorrow.
You. Yeah.
Yes. It's absolutely no problem. I mean, it was not a long time ago since I was a teenager and was used to staying up late. So, so it's absolutely no problem. I mean, for me, it was really nice to be here with you, explaining or trying to have open these discussions about networks, DOCSIS 4.0. So for me, it's absolutely no problem at all.
Great. Yeah, everybody loved it. So thank you again, and have a good rest of your night.
Yes, you too. Have a nice day.